All right, so number 88. Solution is made of mixing 15 grams of strontium hydroxide and 55 milliliters of 0.2 molar. Write a balanced equation. So your strontium hydroxide, we know strontium, well, it even tells you the formula here, so we know that. It says a solution, okay? Well, it has to be a solution in order for it to react and be able to go in, okay? And then the HNO3 is nitric acid. And you have 55 milliliters of 0.2 molar of that, okay? So, which one of these, what are the states going to be on these? Strontium nitrate.
It's a nitrate, so it's going to be aqueous.
It's a nitrate, so we know it's soluble, it's going to be aqueous, right? Okay? And what about water? It's a liquid. Water's not dissolved in water, so we don't say it's aqueous. Water is going to be a liquid. Okay? So, water is covalent. It's not going to break up into ions at all, so we're not going to have any ions of water in here at all. So for part B, how many ions are present? None of this. Okay? All of the strontium that's from here, well, we got to find limiting reactant. Okay? And figure out, but the strontium is aqueous and the strontium is aqueous. So however much strontium you have here, you're going to have that much strontium over there. So I mean, it's not going to change. The total amount's not going to change. Okay? And then the nitrate's the same thing. Nitrate is aqueous here, nitrate's aqueous here, so the amount of nitrate that you start with is the same amount that you're going to end with. Only the things that precipitate out are the ones that are going to change. Okay? So the thing that precipitates out is the OH and the H+. So let's find our limiting reactant. So strontium hydroxide, we take 15 grams, SrOH2, change that to moles, 1 mole over the molar mass, 34 plus strontium is 87.6, so 34 and 87 is 121?
121.6.
121.6. How many moles does that come out to?
0.123.
0.123 moles of strontium hydroxide. Okay? So that's how much of this, and it's divided by 1, so we don't need to divide as far as for limiting reactant. Do the same thing. Now this time we have volume and molarity, so I'm going to take 0.0550 liters HNO3 times 0.2 moles for every 1 liter. Molarity times volume equals moles. So that's going to come out to 0.110.
Yeah. Or
0110.
oh,
0.011?
yeah.
My mental math with my decimals is my weakest area, just knowing how many plays work. When you multiply the decimals, where am I going to end up at? And so that's how many moles of each one, but we've got to divide this one by 2. And this is already, without even dividing by 2, I know that this number is way smaller than that number. You know, if I divide by 2, so I mean, it's a moot point, so I don't even need to do that. I know that this is my limiting reactant. Okay? So that means this is excess. So when all is said and done, my strontium is still going to be in solution, however much I started with. Well, strontium, I started with 0.123 moles. For every 1 mole of this, or 1 molecule, I get 1 strontium. So I know that I started with 0.123 moles of strontium. I know that nitrate stays the same. I know that I started with 0.011 moles of HNO3. So I have 0.011 moles of NO3 minus. So that's how many I'm still going to have here. Okay? But this is limiting reactants, so this is all going to use, so this all goes to here anyway. The only thing that's going to change is my hydroxide. Okay? Because I have some excess here. Some of it precipitated out or formed of water as a liquid. Some got unused.
So water won't split into ions.
Water does not split up, ever. Only aqueous dissociate. Solid, liquid, gas are always together. Only aqueous dissociate. That's a good point. Okay? Solids, liquids, and gases always have to stay together. That's why in a double replacement reaction, and again, we're going to go over this more next unit, but in a double replacement reaction, you have three types of double replacement. A precipitation, a formation of a precipitate, a solid, an acid-base neutralization, which is what this is, where you form liquid water, or a gas-forming reaction, one in which a gas is formed and bubbles out of the solution. So if you make a solid, liquid, or a gas, that means something is happening. If everything's aqueous, then everything's dissociated, nothing really happens. All right, so let's just go through. We can do the strontium. We just said the strontium concentration is 0.123. It didn't change. It's aqueous here, aqueous there, so it's 0.123 moles. What's my final volume?
0.055.
55 milliliters still, right? Because we didn't add, we're assuming the 15 grams doesn't change the volume at all. Most of the time they say that in the problem on an AP question, they would say assume that there's no volume change with the addition of the solid. So what does that come out to?
2.24.
2.24 molar SR 2 plus. Okay, now we can do the same thing on the nitrate. We know how much nitrate we put in, 0.011 moles. All the nitrate that was here ended up over here, so it's however many moles we started with here, that's how many moles we get there. Okay? And it's because of the nitrate, again, conservation of mass. I mean, you don't just disappear. So, we know that it's 0.011 moles. Over 0.0550 liters. And that turns out to equal 0.0200 molar. Yeah, no, 110 divided by 55 is 2. So now the only one that's a trick is my excess hydroxide. We already have the excess strontium figured in. So I have to figure out my excess hydroxide. Okay? Well, I need to find out how much got used. I know how much got made. Well, I know that this is my limiting reactant, so I know that I started with 0.111 of this. What's my ratio here? Moles of HNO3. So then it's going to be 1 mole of SrOH2 for every 2 moles of HNO3. Right? But when this breaks apart, how many hydroxides am I going to get? 2. So I'm going to get 2 OH minus for every 1 SrOH2. Which means, again, these 2's are going to cancel out. So the OH minus that's used how much was given? How do I find the excess OH minus?
Take the molarity of SrOH2 and divide it by 2.
Why divide by 2?
Because there are 2.
Well, how much OH minus did I have initially in solution? 15 grams of SrOH2, right? Which was 0.123 moles of OH2. So So how many moles of OH did I actually have in solution?
Oh, 0.123.
246.
0.246, okay? So I had 0.246 moles given minus the 0.0110 moles used. Is gonna equal, that's gonna be 0.235.
Yep.
So what do I do with that to get the molarity?
Divided by liters.
Divided by 0.0550 liters. 4.28 molar. That one's a little tricky. Okay, because this is, all you have to do is figure your excess. And so excess is always gonna be how much you have, but when in here, the tricky part of this is that in your given, it's OH2. So when that breaks up, so we found that there's 0.123 moles of SROH2, but that means it's gonna be 0.246 moles of OH. How much was given? How much you put in? Minus how much got used, okay? So, we good with that? Maybe? Possibly? Questions? Just know that, I mean, on the quest, based on how long it just took you to do all of that, one at the most, okay? So that's not gonna be the major part of the test, but I mean, it is gonna be a part, you need to be able to do that. You know, you have the basic stoichiometry and all that other stuff that we're gonna look at on that worksheet as well. Okay? So, let me pull up the worksheet.
Wait, you said it's gonna be on Monday?
Test quest is on Monday.
Is it for everyone or? is it-
Everybody. Yeah, so, let me see, this is what today is Thursday, so you're Monday, so you'll be here in class. But it will be it'll be, again, you'll be able to have open notes and stuff because everybody at home will have open notes. So I don't want you to have an unfair disadvantage by having to be here to take it. Now notice on this worksheet that I said it's pre-AP, so I mean, this is just kind of the fundamentals. Okay. Assume 6.73 grams of sodium carbonate is dissolved in enough water to make 250 milliliters of solution. What is the molarity of the sodium carbonate? Well, molarity is equal to what?
Grams per molar mass over liters.
Okay, moles per liter, which is grams over molar mass over liters. So we just plug in 6.73 grams divided by the molar mass. What did we get the molar mass to be? 106? Is it even, 106 even?
105.99.
Yeah. If you said 106, that's 100% fine. that tells me how many moles I have, and I put that into 0.25. What's that decimal point right there mean? 3 sig figs. Okay? So I go ahead and include it there. Now, it's not going to change my number or the answer, but you just need to know you have 3 sig figs in your answer. And that answer turns out to equal 0.254. But when you put sodium carbonate into water, what's it going to dissociate into?
2 sodiums, like ions.
2 sodiums and 1 carbon. Okay? Because it's not going to be Na subgroup 2, because the ions that form are Na plus ions. Ionic compounds, metal and a non-metal, this is a polyatomic ion. An ionic compound is composed of ions, so it's going to break up into the ions. Na2 is not an ion. It's the Na plus, and 2 positive things are not going to bond together. So it's going to be 2 Na pluses. So if I have 0.254 molar of this, for every one of these, how many sodiums am I going to get? So what's the concentration of sodium actually going to be? 0.508, right? Steve. What about the carbonate? 0.254. Notice that the overall concentration of particles is 3 times this, because I mean, if we added these together, we're going to get 3 times this, because every one of these breaks up into 3 particles. Are y'all seeing how they dissociate? Positive ion, negative ion. You have your positive ions here, your negative ions there. I'm a sheep guy. Did I give you this? I never know who I gave what. There's you can have this. And on the back, this is probably one of my best creations. And it's an adaptation of other flowcharts that have been used for naming. But you can name any compound following this flowchart. Every compound has a positive thing and a negative thing. The first thing's positive, the second thing's negative. Okay? So you ask yourself, is the positive thing hydrogen? If the positive thing is hydrogen, then we know it's an acid. And then you have the acid naming rules over here as far as what the anion ends in, and you can tell whether or not it's an acid or not. Okay? If the answer is no, then you ask yourself, is the positive thing a metal? Or the one polyatomic cation, ammonium? So if it's a metal or ammonium, that means that it's an ionic compound. Now we have to ask ourselves, does the metal have more than one oxidation state? So you look on the periodic table, where is it located? If it has more than one, you use a Roman numeral in the name like we talked about with nickel sulfate. If there's only one possible, you don't need the Roman numeral, you just name the cation and then the anion. So if it's not hydrogen and it's not a metal, the only thing left is for it to be a nonmetal, 2 nonmetals combining, and that means it's covalent. We're going to name it with these prefixes. So this is how you can just do all your naming just with 3 simple questions. Okay? So that just kind of gives you a flowchart, reminder. I don't know, those of you had the Mr. Graber, they had a flowchart, and I think even Ms. Guthrie had a flowchart for naming, but it was very convoluted. There was like 15, 20 questions on it. Okay? I like it, keep it simple. This just kind of keeps it short and tells you exactly what you need to do. Okay, and has everybody got the periodic table here? By giving you one of these?
Yeah.
Okay. These are valued.
Okay, thank you. Yeah, I'm prepared.
All right. what is the mass in grams of solute in 250 milliliters of 0.125? So this time, we're solving for grams. So we do our algebra. Molarity is grams divided by molar mass divided by liters. So to get rid of liters, we multiply both sides by liters, right? To get rid of that, that's going to leave you grams over molar mass is equal to molarity times liters. So, well, that's just grams over molar mass over liters. You all are elite math science students, you're in advanced, but sometimes the simple math gets you. Okay? So we know that molarity times liters is going to equal grams over molar mass. So then we multiply both sides by molar mass, so we end up getting liters times molarity times molar mass is equal to grams. Because this is going to be liters times moles per liter times grams over moles. So notice liters cancel, moles cancel, leaves you with grams. Okay? So, simple algebra, just rearranging, solving for G. Okay, but let's make, sometimes the simple algebra is the one that messes us up. But if you're solving for G, you're going to multiply all three things together. Units, again, will tell you, start with the simplest unit, the volume. Then set your units up until you get to grams. So, grams is going to equal 0.250 liters times the molarity, which is 0.0125 moles per liter, times the molar mass of KMnO4, 64 plus, what is that, 54? 54.94.
158.03.
Thank you, 158 point what?
03.
So all of that equals 0.494 grams. Now, the green crystals that we were supposed to make today are called potassium trisoxyalloferrate 3 trihydrate. Okay? At the end of the year, assuming we're still in school, who knows? Nowadays you just never know, right? And so at the end of the year, we'll go and we'll test the purity of our potassium trisoxyalloferrate 3 trihydrate by titrating it with a standardized solution of pretty potently poisonous purple potassium permanganate. That'll be the title. That'll be the title of your lab.
Where does that come in on the naming sheet?
Yeah.
Well, the pretty potently poisonous purple part actually takes me back to my chemistry 2 class as a junior in high school in Columbus, Ohio. And we were doing something, there's 9 of us in the class. And that particular class, just so you know, was no test, no homework, and A or an F based upon participation.
That's kind of nice.
Yeah.
Yeah.
It's just there to learn, okay? So it was a semester-long class, and so it was good, but we just we're doing something with KMnO4, and we try to figure out how many P's we come up with for the alliteration, and somehow or other, that's one of the few things from high school that has stuck with me, is pretty potently poisonous purple potassium permanganate, because it's a deep purple colored solution. And so, anyway, it's really just called potassium permanganate, which would fit as far as is the positive thing of metal, yes, potassium. Does potassium have more than one oxidation state? No, so you just name the positive and the negative, potassium permanganate.
What about the other thing that you said?
Potassium trisoxyalloferrate 3 trihydrate. Now that is what we call, it has a complex ion in it. It is K3 potassium trisoxyalloferrate trihydrate. Okay, so that's what we're going to make. We're supposed to make that today, but we don't have any oxalate. Potassium oxalate disappeared. Okay? But this is what we call a complex ion because it's composed of 2 ions. The Fe, this is Fe3 plus, this is 2 minus, so we have a total of -6 and plus 3. So this is, Come on, Steve, do math. It's got a -3 charge on the complex ion. Because we have the -2, so -6 from this part. Iron trisoxylattoferrate 3, the Roman numeral 3 is telling me that it's iron plus 3. Okay? So, that's why it's going to take 3 potassiums here. So it's really a positive thing and a negative thing. The negative thing is just a complex ion, which makes the name more complex, and then trihydrate. Just like we've named the hydrates already this year. Okay? Now, that's just a fun thing to say. Potassium trisoxylattoferrate 3 trihydrate. All right. I should have you guys come up and put these on the board, the last ones. So pretty straightforward. All right, I'll do number 3, and then you guys, we'll put 4 or 5, and it goes to 7, doesn't it? Yeah, I'll have you guys put the rest of them on the board. But this one, I just want to make sure we understand percent yield. How many grams of silver carbonate could be formed if a student mixed 50 milliliters of 0.250, so we have 50 milliliters of this, 0.250 molar. And I want to know how many grams of silver chromate. Now it says excess K2CR4. What does that tell me?
The limiting reactant is the other.
That's my limiting reactant. I just know I have excess of this. I don't care how much excess. I just know I have plenty to react with this. This is going to run out first. And the question is, how many grams of this? This is a dark red, kind of tomato juicy colored solution. Okay? So, what do?
You find the grams of AgNO3.
Do we need to go to grams?
Oh wait, you find the moles. So
You can go to find the moles, right? Because the first step of any stoichiometry is just convert to moles. And so we're going to start with 0.0500 liters of AgNO3. Always start with the simplest unit. The molarity is my conversion factor. That tells me how many moles of silver nitrate I have. And then what? Mole ratio. 1 mole Ag2CrO4 for every 2 moles AgNO3 times right?
Yeah.
Well, hey, that's okay. You have to check me because I've been making mistakes left and right here. So, so now I'm going to go 64 plus 52 plus 107.9 times 2. All that comes out to 331.73. And again, if you just use 331.7, that's 100% fine. It just, you guys, I think we need to use at least 3 or 4 sig figs of molar mass. Okay, I used to be a 3 sig figure. I've kind of converted to a 4 sig figure of molar mass. You never want the molar mass to be your limiting sig fig. Because we have access to way more sig figs on the periodic table, you don't want, since this is 3, we want to at least have 3, preferably 4, so it just gives a little bit more accurate value. And all of that turns out to equal 3.07.
No, 2.07.
2.07 grams of silver carbonate. Now, that's how much you get if you did everything 100% right. Didn't lose any. This is what we call the theoretical yield. Stoichiometry always gives the theoretical yield. How much possibly, how much could be made? How much could be formed? That's the maximum amount. Assuming you didn't lose any, you didn't spill any, none stayed dissolved in the water, assuming everything was perfect, okay? But what is percent yield going to be? It's gonna be what you got divided by my theoretical yield, and then times 100. This is my actual yield. That's what we really got. Okay? You can call it the experimental yield, experimental value. It's what you got in the lab. Okay? Generally, it's going to be less than what you're supposed to get because usually we spill some, leave some in the beaker, you know, different things happen. If it's still wet, if when we collected it, we didn't dry it completely, it's wet, we might get over 100% yield because the water in there is going to add weight and you have more than what you're supposed to because you have an impurity in there, water or some other impurity. So we're going to say 1.50 grams divided by 2.07 grams times 100. What's the percent yield turn out to be?
72.5.
72.5. Okay? So that's how you calculate percent yield. Now, you're going to be required to know this equation. Okay, that's not used over and over, and that is a question they ask a lot of times on the AP test. Just calculate percent yield and go from that. It's super simple. This always comes from stoichiometry. This almost always is given, or from lab data. You have some data, and you can calculate it from that. We're going to do this. We're supposed to do this today. I was going to introduce this concept with the calculations from today, because we're going to make our potassium trisoxyl 33 trihydrate. We're going to collect, dry it, and filter it, dry it, and weigh it. But then we want to know, well, how much should we have gotten compared to how much did we get? And calculate our percent yield. So we'll do that next week, assuming I can spend money. We're not supposed to spend money in September.
For like the percent, you would follow like the rules of sig figs too?
Yes. Yeah. Now, the times 100 doesn't count though. You know, because that's an exact thing. Okay? All right. Who's going to be the, who got left out last time?
I'll remember all.
4, 5,
Okay.
7, 6. You'll do 6? Okay, good. Keep knocking.
Wait, am I doing 5? Yeah, you're doing 5.
No, we don't.
Yeah, okay, good. Either 4 or 5.
Okay, let's start. Let's do them in order: 4, 5, 6, and 7. Do we need more markers? There's a blue one right here. That's what I got.
Yeah.
Do we need to write the whole equation, or should we just?
Just do show your work that's needed for it. If the equation's on,
It's already on.
if it's on there, then you don't need to show it.
Really?
But I got three.
We talking about number 4?
Yes, sir.
Maybe I did it wrong.
I got milliliters.
I got 314.
That's what I got.
That's fine.
I got 37.
But it's in mill.
See, like, but I think I did the same thing.
Okay, so,
Oh, hold on, I didn't use the molarity, hold on.
yeah, this is where it's messing up at.
Yeah, hold on.
See, I got,
What did y'all get for number
yeah, I just.
I'm not supposed to use the molar mass, I'm supposed to use
See,
the
I just did
molarity.
it
Right.
because I
Okay,
just,
hold on.
So, and then,
So,
I asked.
do we have the balance equation is 1 to 1?
So, yeah.
yeah, it's 1-to-1.
Okay,
So I
so,
think here.
Yeah.
See, I don't know where this is.
okay, so what is molarity?
I checked with this one for,
molar mass.
that's the only one that.
Well, it's gonna be
I
moles
guess you got that.
over liters,
Oh, what did you
right?
get for number
Yeah.
5?
This will
You
give
get
you
50.0.
moles.
No, I got 25.0.
Yeah.
Because,
We all got something
Just
different.
divided by the given volume.
Really?
What'd you get for
So
number
we're given 1.5 molar.
Oh, okay, so, then times, then,
Yeah,
yeah,
so times,
times so many,
so
Go ahead.
0. So would it be?
what, you want moles on the bottom?
Am I
Yeah,
doing
so
this
0
right?
times 1 times 0 moles over.
1 liter
and
equals.
equals, I don't know. What is that, y'all?
Oh.
The answer?
314.
Well, it's gonna
So-
be 314, but then I also have to get a milliliter.
Yeah, so it's 0.314 liters?
Yeah, yeah.
And then
So
3.
It's-
then,
No, you know, 0 is 0.314 liters. Liters,
oh, yes, so
well,
liters,
yeah.
and then,
which you can just, and again, you can show the work times 1,000, or you can just do it in your head and just say it's 314. Okay? So,
okay.
all right? Now, the reason why, again, I grade homework on completeness, because I want you to have the ability to be wrong and not stress about it. It's okay to make mistakes. We figure out that's what we're doing now, is we're correcting and figuring out what we did wrong. Okay? So to go, once we have moles, to go to volume, molarity times volume equals liters. Pardon, molarity times volume equals moles. So then molarity divided by molarity, liter, moles divided by molarity is going to give you liters. Okay? The whole point is molarity is the conversion factor between moles and liters, whichever way you're going. Okay? So that's number 4. What do we think? Is number 5? We all agree on number 5?
What did you get for number 5 right now?
I think
Any questions on number 5?
I didn't think the equation was balanced.
They all got something different, like all of
Yeah,
us.
I got.
What did you get?
I got 17.3.
Okay, what's the equation?
Yeah, I had to balance the equation.
Yeah, the equation wasn't balanced, but then I wasn't sure if we needed to balance it or not.
You always have to balance the equation. So what's the equation?
Well, it was like half balanced, but like, okay.
Oh, yeah. I didn't
It was
understand.
NaOH plus H2SO4,
Okay, I got it.
yeah.
So you had to put it to
Yeah.
first.
So, yeah, that's what I was
Okay.
confused about.
So, to calculate the grams, now, did we really need to go to grams here?
No.
Because what was the very next step that this person did?
Since we're right.
Okay?
Good.
Went back to moles. So we could have just gone molarity times volume. Now, it's not wrong doing it this way. This is just an extra step. Okay? It's 100% right, it's just extra work. Because again, we know the molarity, we know the volume. Molarity times volume gives you moles of Na2SO4. Okay, you went to grams and then went right back to moles. Okay? So this times this would have given you the same answer. Then your mole ratio, this is where it's going to be different. The mole ratio needs to be 2 moles of NaOH. And then times your 40. So this is just going to be twice this. So it's going to equal 0.690. Is that what you guys got?
I didn't go 2 grams of that, I just went some moles of NaOH and did the molarity like that.
Okay, oh, so what's the question's asking for how many liters of NaOH are required?
Yeah.
Okay. Yeah, So again, same thing as here. We don't have to go to grams and use that when we want to go from moles to liters or molarity. The molarity is the conversion factor between moles and liters. So all we have to do right here is you have moles, 2/1, then we can use the molarity of 0.5, 1 liter over 0.5 moles. Right? I'm dropping everything. Now, none of this is wrong. It's just extra. Are we not getting that?
No, I get it, I'm behind on writing it down, so like.
Okay. If we want to just do this in a simplified shortcut, okay? Now, again, you do this on a test, you get 100%. I'm assuming, well, you didn't balance the equation, so you're going to miss it, that 2, but everything else seems to be right.
So you just multiply the answer by 2?
Should be, but let's just see how it works out. So, I'm just going to work the exact same thing. So I'm going to start with 0.0500 liters of my H2SO4 times the molarity, 0.250 moles for every 1 liter. That's going to tell me how many moles of H2SO4 I have. Well, I need 2:1. 2 moles NaOH for every 1 mole H2SO4. What's that going to leave me?
Moles of NaOH.
Moles of NaOH. But the question's asking for liters. So how do I go from moles to liters? Well, molarity. Okay, that's the point that I'm really trying to stress here. Molarity, moles to liters, liters to moles. So, I'm just going to put my molarity that's given, it's 0.5, right?
Mm-hmm.
So 1 liter over 0.5 moles. So that turns out to equal how many liters?
0.0500.
0.0530?
00. It's just 0.05.
Oh yeah, because this is 2 times that makes 0.5 divided by 0.5. So it comes out to 0.05 liters, but the question asks for milliliters. Now this is an important thing. Always go back when you get an answer. Go back and make sure you're answering the question. Okay? So this is liters of NaOH, and we can do this conversion in our head. It just goes to 50 milliliters. Okay? Now, I'm not sure where she went off on this one.
I did a lot of gram stuff, so I
Yeah.
don't know.
Okay? And so somewhere a number got off. Okay? So, this is a volume to volume, so you're doing molarity and molarity as your conversion factors, your given and your unknown. All right, what about number 6? We good on number 6?
I got something different on number 6.
Okay, so again, we're given 130 grams. 1.30 grams. This is my unknown. So this is this is my given. This is my unknown. So I'm going to go grams to moles, and then moles times 2. Where does that times 2 come from? Because it's 2:1, right? Now I would prefer you go ahead and use a mole ratio, 2 moles over 1 mole. You show your work, you get credit for that, but I think you'll get lost in the long term. So that's how many moles. So then we have this many moles, 0.125, where do we do here? Is this just transposed by accident? Is this supposed to be 0.125 right here? Oh, it's this right here. Okay? Oh, okay, so this is the molarity. 0.125 is equal to this many moles over however many liters. So then these two are just gonna swap places doing the algebra. So it's gonna be 0.0152 divided by 0.125, and that's gonna come out to equal 0.1216 liters, change that to milliliters. That looks right to me. You seeing where you maybe messed up? Okay, now listen, this is our chance to fix. I don't give homework. Okay, now with virtual, it's not homework, you're doing it during class time, okay? Generally, this is our time to learn, what do I know, what am I good at, what am I still struggling with, and let's ask questions and make sure we're figuring out what we're missing. And then number 7 looks way more straightforward. Molarity times volume times mole ratio times molar mass gets you grams. All right. Tomorrow we'll probably have you doing some kind of review questions, or I may have you start reading some of the book for the next unit.